Now I want to continue on with the example that we just finished in the previous recording. Did an example of two capacitors wired together in series, and we charged them up, found out how much charge each one stored, what the potential difference across them was. We found out that the capacitors ended up both storing, because they were in series, the same amount of charge, which turned out to be 24 microcoulombs each, for a total of 48 microcoulombs. Now, what I'm going to do, although I didn't quite phrase it this way, what I'm imagining doing is taking those two capacitors that we just charged to 24 coulombs each, and then hooking them together in parallel. Now, what's going to happen, and so I've made the drawing here. What's going to happen is that the capacitors now, being wired together in parallel as they are, we discussed a few recordings back that now the potential drop across each of them has to be the same. So it's going to have the same potential drop, same V for each of them. But their capacitances are different, and therefore the amount of charge that they can store is going to be different. The amount of, or I should say, the amount of charge that they will store is going to be different. Okay, but the at the moment that we first hooked them up, they're both storing the same amount of charge. That was fine when they were in series, but as soon as I put them in parallel, that becomes an unstable situation. Okay, and the reason is simply that because they have the different capacitances and the same amount of charge, that at least initially when we first connect them, their potential drops are going to be the same, are going to be different across each. Same charge, different capacitances, different potential drops. But wired together in series, wired together in parallel, that can't be the case, not when the situation is stable, which means then, in short, that when I hook these two already charged capacitors together, that the charge from one of the capacitors is going to move to the other capacitor. It's basically going to move from the capacitor that has the smaller capacitance, the smaller capacity to store charge, to the one that has the larger. And again, notice that I'm thinking through the physics before I haven't even read the problem yet, hardly. I'm thinking through the physics before I start digging around for equations. You've got to understand what's going on before you start calculating. Otherwise, you'll really mess up. All right, so our expectation is that at the end, at a stable equilibrium state, the potential drops will be the same across each of them. But the initial situation isn't that. The initial situation has different potential drops for the two capacitors because they're storing the same amount of charge with different capacitances. So the charge will redistribute itself. We expect that the 4 microfarad capacitor at the end of things will end up storing more charge than the 2 microfarad capacitor will end up storing. Okay, but they will end up with the same potential drop. Frankly, it takes longer to analyze the problem than it takes to calculate it, but if you don't analyze it first, you'll never calculate it correctly. And as you're going to see, as you've already seen, the calculations are trivial. And what a horrible thing it would be to lose a bunch of points on such a mathematically simple problem just because you didn't think it through before you started. All right, but we did. All right. Potential drop will be the same across each. Must be the same. Okay, so the potential drop across a capacitor is obviously related, calculated like this. But in this case, the capacitance that we're talking about is the equivalent capacitance, okay, of the two capacitors. The equivalent capacitance, remember, for parallel is simply the sum of the two capacitances, which is 2 microfarads plus 4 microfarads, 6 microfarads, okay? That's equivalent capacitance. And so the potential drop is now, this is, again, you've got to think it through. You've got to know what you're talking about. We've got the equivalent capacitance is a result of two capacitors wired together in parallel. The amount of charge that is stored on the two capacitors is 48 microcoulombs. Sum of how much charge is on the one plus the charge of how much is in the other. Now, it is true that at equilibrium, after the charge has rearranged itself and so on, the two capacitors, after everything is done, the two capacitors will end up storing different amounts of charge. They started out with the same amount of charge, but they ended up with different amount of charge. But the total amount of charge will remain the same. It has to. Conservation of charge. And indeed, this whole problem is an example of conservation of charge. The previous problem in the previous recording, conservation of energy. This is conservation of charge. We still have 48 microcoulombs of charge total. It's redistributed. One of the capacitors is going to hold more than the other one is going to have after everything is settled down, after equilibrium is reached, but it's the same amount of charge. And I'm making a big issue of that because now we're going to substitute numbers, and Q here ends up being 48 microcoulombs. The equivalent capacitance we just said is 6 microfarads, and so 48 divided by 6, of course, is 8 volts. And so that 8 volts is the potential difference that will be across both capacitors, each capacitor, I should say. Okay. They'll both have the same potential drop after equilibrium has been reached, and that will be 8 volts. And as promised, the charge on each will be different. We expect the charge on the smaller capacitor to be the smaller amount of charge. So Q1 is going to be the capacitance of capacitor number 1 multiplied by the potential drop that both of them will have. And so that's 2 microfarads times 8 volts, and so 16 microcoulombs, whereas for Q2, C2 times V, that's 4 microfarads because it has a bigger capacitance, and it can store, of course, since it has twice the capacitance, it can store twice the charge. And you'll notice that again, 16 plus 32 is 48 microcoulombs as promised. Once again, conservation of charge. Okay? So a takeaway lesson from this, a couple of takeaway lessons. One, these problems are not difficult. They're trivial as a mathematical matter. Okay? But, and I've already said it 18 times, here's number 19. You've got to think about what is going on physically before you start fiddling with equations. If you don't, you will never get these problems correct. Okay? And there's noticeably more complicated questions I can ask once you know the potential drop, once you know how much charge is stored. There's all sorts of other questions I can ask that are related to those. Okay? But if you don't get this started right, everything else, of course, will be wrong as a consequence. You've got to think through the physics. Think about what is happening, why the charges are going where they're going, why the potential drops are the same in one case or the potential drops are different in the other case. You've got to understand the physics in order to get the math right. Okay? And I think I've beaten that to death, although if you think that's the last time you're going to hear this, well, you probably don't think it's the last time you're going to hear this. Okay. Now, having done capacitors, we're going to repeat the entire sequence of the last few recordings that we did for capacitors. We're going to repeat all that for resistors.